Section 2.4, Real Zeros of Polynomials. Part 1, the Rational Zeros Theorem. The Rational Zeros Theorem tells us that if f of x is a polynomial of degree n, where n is at least 1, and all of the coefficients are integers, then if r is a rational zero of f, r is the form p over q, where p is a factor of the constant term, and q is a factor of the leading coefficient. So what does this mean? First of all, a rational number is a number that can be written as a fraction. So integers are all rational numbers, fractions, decimals that either terminate or repeat are rational numbers. Things that are not rational would be like a square root or a decimal that goes on forever without repeating. So this theorem will only help us find rational zeros of a polynomial. So to find these rational zeros, we're going to look at the factors of the constant and the factors of the leading coefficient. So if I have the polynomial f of x equals 6x cubed minus 3x squared plus 2x minus 4, what I need to do is find the factors of the constant and the factors of the leading coefficient. So the factors of our constant, which is 4, are plus and minus 1, plus and minus 2, and plus or minus 4. And the factors of 6, which is our leading coefficient, are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So to find the potential rational zeros, we're going to write the factors of the constant divided by the factors of the leading coefficient. So to start with, we're going to divide all of these factors here, 1, 2, and 4, by 1. So we have plus or minus 1 over 1, plus or minus 2 over 1, and plus or minus 4 over 1. Now we're going to divide them all by 2, the next factor of 6. So plus or minus 1 over 2, plus or minus 2 over 2, which is 1, we already have that, and plus or minus 4 over 2, which is 2, and that's already on our list. Then we'll divide all of those by 3. So we have plus or minus 1 over 3, plus or minus 2 over 3, and plus or minus 4 over 3. And then we'll divide them all by 6. Plus or minus 1 over 6, plus or minus 2 over 6, which is 1/3. We already have 1/3. And plus or minus 4 over 6, which is 2/3. We already have 2/3 also. So these are our potential rational zeros. That means that if this function has a rational zero, it is on this list somewhere. Let's try another example. Use the rational zeros theorem to make a list of possible rational zeros of this polynomial. F of x equals x to the 4th minus 9x squared minus 4x plus 12. So let's make that list. Our factors of 12 are plus and minus 1, plus or minus 2, plus or minus 3, plus or minus 4, not 5, plus or minus 6, not 7, 8, 9, 10, 11, but then 12. So there's our factors of 12. And the factors of our leading coefficient is 1. So our factors there are 1. So we need to divide all the factors of 12 by 1. So our list is just 1 over 1, 2 over 1, etc. Make sure you write the plus or minus in front of each. So those are our potential rational zeros of this polynomial. Now let's use the remainder theorem to show that x equals 2 and x equals negative 2 actually are roots of this polynomial. So they are on our list of potential rational zeros. Let's see if they actually are. So the remainder theorem says that if we substitute 1 for x, so we find 1 for x and we get 0, that means our remainder was 0, and x minus 1 is a factor, 1 is a root. So if I substitute in 1, I get 1 to the 4th minus 9 times 1 squared minus 4 times 1 plus 12, which is 1 minus 9 minus 4 plus 12. And 1 plus 12 is 13. Negative 9 minus 4 is negative 13, so we get 0. That tells us that 1 is a root of this polynomial. We can do the same thing with negative 2 to show that. So negative 2 to the 4th power minus 9 times negative 2 squared minus 4 times negative 2 plus 12 equals negative 2 to the 4th power is positive 16. And then negative 2 squared is 4, and 4 times negative 9 is negative 36. Negative 4 times negative 2 is 8, and then plus 12. So 16 plus 8 plus 12 is 36, and 36 minus 36 is 0. So negative 2 is also a root of this polynomial.